Okay, welcome everybody to the annual J. Modi Memorial Lecture. I'm Cyrus Mankaridis from Computer Science, and I'd like to thank everyone for joining us to remember our lost colleague. As is customary for the J. Modi Memorial, we award an award to one of our top graduate students, usually a PhD student. And this year's winner is Ling Bai, who's here. Congratulations. Ling is a doctoral student of David Breen, who's here with us. And she is a candidate doing her PhD in computer science. And her work is in geometric biomedical computing, and she has a master's degree in computer science and a bachelor of engineering in computer science and technology. Her research focuses on modeling and simulation of self-organizing shape primitives whose behavior is inspired by cell biology. This is quite interesting. And one other point about her research is that she spent some of her time, 8 months, at Germany's Max Planck Institute for the Physics of Complex Systems as a visiting scholar with David Breen. And I'm not sure if you're going there again this summer. No? 1 year is enough. So apart from being a very bright student, excellent in her classes and making terrific progress in her research, she also has spare time for, beyond the typical socializing of a graduate student. In her spare time, she's raising her 18-month-old daughter, Genevieve, and she has told us that she hopes that Genevieve will become a scientist when she grows up, and maybe a computer scientist even. All right, so I'd like to invite you up to receive your award. Okay, so every year at the J. Modi Memorial, we have an invited speaker give a talk, and we try to find speakers who have had some connection to J. Modi. And this year, when we were going through our potential list of people to invite, we came across Dr. Peter Stone, who has a connection obviously with J. Modi. They overlapped in some of the labs. But interestingly enough, there was a connection of Peter's when after we invited him, he told us that his sister is on the faculty, Mira Olson, and so that was a fortunate coincidence. Peter Stone has many titles. He's an Alfred P. Sloan Research Fellow, a Guggenheim Fellow, a AAAI Fellow, a Fulbright Scholar, and a professor in the Department of Computer Science at the University of Texas at Austin. And before that, he was at AT&T Labs Research in the AI group there. He received his PhD from Carnegie Mellon University in 1998, master's in 1995. And the connection with Jay, or one of the connections, is his PhD advisor was Manuela Veloso, the second J. Modi lecturer in our series, and also J. Modi's postdoctoral advisor. So Peter Stone is well known for many things, but what I know him mostly for is for his huge success in developing teams of soccer robot agents. And he has won 6 robot soccer tournaments in simulation and with real robots. And I asked him a few minutes ago if he was going to cover any of that in his talk, and he said yes. And I think that's an excellent thing to cover in the year of the World Cup that's happening in Brazil this summer. He's the author of Layered Learning in Multi-Agent Systems, a winning approach to robotic soccer, and he's the co-author of Autonomous Bidding Agents, Strategies and Lessons from the Trading Agent Competition. In 2003, he won the Career Award from the NSF, And in 2007, he was awarded Ichikai's Computers and Thought Award, which is given only once every 2 years to a top AI researcher under the age of 35. In 2004, he was named the ONR Young Investigator for his research on machine learning and physical robots. So, highly distinguished scholar, and we're very happy that he's here to help us honor Jay Modi. Would you all welcome Peter Stone?
Thank you very much for the kind introduction, and all of you for coming. It's an honor and a pleasure to be here, and especially to be talking in the Jay Modi Memorial Lecture Series. I did know Jay quite well. He was the kind of person who was just full of energy and enthusiasm, and I remember in his early years, probably his first or second year as a PhD student, he was giving a demonstration at a conference we were at, Autonomous Agents and Multi-Agent Systems, and it was clear already then that he was just full of energy and creativity. He was working in some of the RoboCup, Robot Soccer. He was actually doing RoboCup Rescue, a disaster rescue sort of branch of RoboCup. And I followed his work through while he was a graduate student and a postdoc, and it was really a sad tragedy certainly for the department, but really for our whole field when he passed away. So it's an honor to be a part of this series, and thank you all for being here. So I'm going to talk today about learning and multi-agent reasoning for autonomous robots. And I'm going to start by just giving a brief overview of where I think we are in the field of the broad field of robotics. And to do that, I'm going to step back and talk about the field of just computer science. And there's sort of this series of well-known quotes and projections, or early projections for the field of computer science, or just computers in general. This one is widely attributed to Watson, the founder of IBM. I think there's a world market for maybe 5 computers. Turns out this is apocryphal. There's no evidence that he actually said this. But it was plausible at a time when computers were, filled an entire room and were vacuum tubes and were, very, very large beasts in some sense. And around the same time, this one is not apocryphal, it's actually documented something similar. It's very possible that one machine would suffice to solve all the problems that are demanded of it from the whole country. So now one computer, this was by Sir Charles Darwin, the grandson of the Sir Charles Darwin that you're probably thinking of when you see his name. But he was head of a research institute in charge of researching the possibilities for computing in Great Britain. And then in 1977, the chairman and founder of DEC, Ken Olson, said there's no reason anyone would want a computer in their home. Now again, this is also often taken out of context. He was talking, he actually did have a computer in his home, but he was talking about you wouldn't want computers controlling your garage door or the light switches or things like that. And of course, even that has also now turned to be sort of maybe a lack of foresight to say that. More recently, of course, we're all familiar, we live in a very different world. It would be crazy to say things like that. There were estimated 1 billion PCs in the world in 2008, close to 2 billion in 2014, plus tablets and smartphones and now wearable computers, people wearing them on their, on their eyes and on their wrists. And this has all been enabled by a lot of computer science research, by in many different areas of computer science, systems, networking, programming languages, HCI, artificial intelligence. It's sort of taken the whole field to do this. And just to look into sort of the typical growth curves, this is showing units shipped per year, so it's not the number in existence. And this is a log scale on the left axis here, and the y-axis. And so, we're looking back, and I don't know if you can read the numbers here, but in the mid-1970s, we're talking about 10,000 shipped per year. And now we're talking about the last quarter of 2013, I read there were more than 50 million iPhones sold. Right? So it's just, a huge sort of exponential growth curve. So now let me shift. This is computers. This talk is actually about where we stand in robotics. And so this is a similar graph. It's a slightly different number. This is operational stock, so not just units shipped, but actually units that are in existence of industrial robots projected from 2011 to 2016 in various parts of the world. And we're in the 500,000 range. So on this graph, we're still sort of around here. And industrial robots, the things that are actually charted on this graph, typically are in pictures like this, are in sort of settings like this one, where they're in a very self-contained room. You wouldn't let a person anywhere near them, very dangerous, or people are worried about safety concerns, manufacturing cars and things like that. Now, there have been some changes in the field. This is a system called Kiva Systems that was bought by Amazon recently, and these are robots that are transporting the kinds of transporting the shelves that when you place an order to Amazon.com, the robots bring the shelves to the person who packs the box rather than the person walking around the warehouse. And so this is sort of a new direction for industrial robotics. And there's a company, Rethink Robotics, that has now introduced this Baxter robot, which is also designed as an industrial robot, but designed specifically to be in an operational space with people and dealing with things like compliant control, being careful, not the safety issues are not a huge concern, and also the much more friendly human interfaces so that you can teach the robot. But really, to be able, this is all industrial still, and to be able to go to this point of having millions or hundreds of millions of units shipped, it's not going to be due to industrial robotics. At some point, the robots, if and when this happens, it's going to have to be by penetrating the home markets and the sort of common spaces towards ubiquitous robots. And there was a first play towards this, I think was a great one, the iRobot's Roomba and other now vacuum cleaning robots. This sort of made a dent. They're inexpensive enough that people could buy them, but they didn't really pass the test of, or at least so far, pass the test of the appliances, like refrigerator and a microwave. Not everybody needs a vacuum cleaning robot in their house. So it was sort of a first step, but we still haven't gotten to that sort of killer app for robotics that would really make them really ubiquitous. The other thing happening is there's now many companies that are developing remote telepresence robots, and so maybe this is a direction, and we still haven't seen how much this will develop, but where people can telecommute and have sort of their face and their presence be wandering, moving around in an office environment. I believe strongly that this transition is going to happen, that we are going to get to a point where there are going to be robots everywhere. But this is going to be, and we were talking about this at the table here before I started, it's not going to be able to happen due to the advances in one field. This is going to be due to multidisciplinary research. It requires things that span areas such as motors and control, locomotion, compliant motion, things that typically happen in mechanical engineering departments. There's things that typically happen in electrical engineering departments, and of course computer science departments and schools of information. And so it's a really, to cover the area of robotics, it sort of requires a pretty broad span of research. And just to give you, this is just a small list of the areas, just to give you a view for those of you who haven't been following some of the things that I've found most impressive recently. This is a robot from Boston Dynamics, which has recently been purchased by Google, as many companies have been recently. But this is actually a robot. It's not an animal dressed in a suit. This is a running robot, and I find this very impressive. The kind of speed and agility that they're able to show. It's a very loud robot. And it uses gasoline. It's a gasoline run. So it's not the kind of thing you'd want to have walking around in your house, but it was developed for military purposes. This is a robot riding a bicycle, which I found pretty impressive. One of the areas that sort of have stopped robots from becoming ubiquitous so far is that I mentioned Kiva Systems brings the shelves to people when they're packing boxes, but you still need a person to pack the box, and that's because we haven't quite gotten, or we haven't really gotten very far to the fine motor manipulation or fine control. But this video by my colleague Peter Abeel at Berkeley, I think, shows some nice progress. They were able to take just a pile of towels that was plopped down on the table, and the robot's able to, this is a PR2 robot that was made by Willow Garage, and it's able to fold them into a neat pile of 5 towels. Now, to be able to watch this video, it had to be sped up 120 times. Okay, so that's not something that's happening very, very quickly. But this is obviously a room for improvement and would have a lot of impact. Something that's going on right now is the DARPA Robotics Challenge, where they have robots that are trying to do a whole bunch of different tasks. This is a robot driving a car. It's not a robot car. It's actually a robot that has to get into the car and drive it. Same robot. This is the team that is, I think, it's currently in first place at the DARPA Robotics Challenge, although they were just also bought by Google, and it's not clear that they're going to keep going. But the robot had to do a whole bunch of tasks, like walking up a ladder, like I showed, driving the car, walking over terrain, clearing debris. These are, sort of, again, big tethered robots, but it's sort of we're broadening out the kinds of tasks that they can do. They had to be able to walk up to a door and open it. I think there's 2 other tasks. One of them is turning a valve, so I think that's the next one that'll be shown here. Or no, actually punching a hole in a wall with a power tool. And then I think after this one is turning a valve as well. So and so this is ongoing. It's a competition being. Oops, sorry. Sometimes my videos don't stop. It's an ongoing competition being held by DARPA, sort of akin to the DARPA Urban Challenge or Grand Challenges that you may have been familiar with in the past. Actually, I had a team that participated in the DARPA Urban Challenge, which was for autonomous cars. This is the car here in the back was our car that was participating. This is the semifinals of the 2007 DARPA Urban Challenge. So there's no person in this car, and these cars here are being driven by people wearing helmets. They were sort of scared. But it had to make a left turn across traffic, so find a gap in traffic, make a left turn, then come up to here, make another left turn, and it did 8 loops around there in about 20 minutes. So that may be one of the, or is likely to be one of the biggest penetration points for robotics in the near future as autonomous cars. Just to see what they can do, this is sort of the extreme version of that. Here's how you may see cars parallel parking in the future. It's a colleague, Zico Coulter from Stanford, who controlled this autonomous car to automatically fit into a parking spot. So these are the kinds of sort of capabilities of robotics right now. But to get to, from sort of these low-level capabilities and to get to the robustness that we need for robots to be ubiquitous, we're at a point where there's still a lot of need and opportunity for the basic capabilities that are going to transform robotics from sort of a series of neat videos to actually being ubiquitous. And part of that is going to be determining what are the applications, what are the things that they're going to do. And so there's a lot of opportunity to enable and enhance existing applications and come up with new ones. And so this is a small list of the kinds of things that seem like some of the likely influence points. And so this talk so far, all that so far is basically by way of introduction. I was talking about the field of robotics as a whole. What I want to do with the remainder of my time is talk about my small part in this sort of overall endeavor that's really too large for any individual researcher, or even really, as I said before, any individual department. And my focus has been within computer science to bridge the gap between theory and practice, and to start with some of the computer science algorithms in artificial intelligence, specifically the kinds of things that Jay was very focused on, agent-based systems and multi-agent coordination, and take that towards how do we get robots to actually cooperate when we're dealing with real robots in the real world. And so I am going to talk about 2 particular applications, robot soccer and autonomous driving. And whenever you have a talk of this sort, there's always a choice. I could go, sort of deeply into one algorithm that we've developed and talk about sort of, the nuts and bolts all the way down to the equations. I thought for this occasion and for this kind of audience, I instead would give a much more sort of broad overview of the kinds of things that we've done in my lab. But I'll be happy, given this sort of small audience, I'll be happy to stop and take questions or be interrupted, or certainly, I'll be here afterwards and can go into much more detail. And all the things that I'm talking about there, of course, are papers and on our website with all of the technical details. So one goal of AI and robotics is to create robust, fully autonomous agents in the real world, and I've been sort of motivating that up to this point. But a question then becomes, how are we going to do that? One possibility is, and this sort of the approach that the field of artificial intelligence took from the beginning was, well, let's break down the task and work on each of the components individually. Let's work on language, and let's work on planning, and let's work on manipulation, and let's work on locomotion and vision, and all as separate subfields, and then put them together magically at the end. You can tell as I'm saying it, I think this is not necessarily an approach that magic part is actually doesn't come for free. I think it's important that we do need to have this sort of these focuses in these individual areas, but I think it's also useful to have some of the field thinking from the other direction. And in particular, building complete solutions to relevant challenge tasks, so that you have to, from the start, think about how all these pieces will fit together. And there's been a lot of actually work in the areas of robot motion planning and AI planning that are at completely different levels of abstraction, and there's always been the assumption that they could be put together. People from both fields are now realizing that, no, we're actually going to need to spend a lot of time rethinking both areas before they come together, and Chris knows this very well. It's been a part of the community that's been thinking about this. So what I mean by building complete solutions to relevant challenge tasks is, first of all, by complete agents, I mean computer programs that sense the environment, decide what to do, and act in a closed loop without a human involved. And by challenge tasks, I mean not just being able to get the robot or the computer program to exist without crashing, without falling off a cliff, but actually to accomplish some specific concrete objectives. And so what we find is by doing this, and the goal of this style of research is that it will sort of be a pull on help us recognize where we have greater need for new algorithms and new theoretical advances, and it can play well with the sort of bottom-up style of research that I was talking about. Now, my experience, the problems I've worked on that I'm going to talk about here, has been that there's been a lot of motivation for improving the state of the art in two particular areas. If you're going to create complete solutions to relevant challenge tasks, you need to allow them to be able to improve from experience, the subfield of machine learning. If you have an autonomous car and it backs out of your driveway and goes through the same pothole every day, you're going to have a hard time calling it intelligent. And similarly, if you have an autonomous car, your neighbors are probably going to have one too. They're going to need to pass each other or interact with each other or yield to each other on the road. And that's the subfield of multi-agent systems. How do autonomous agents interact with one another? And so I'm advocating here in the style of research that I'm going to illustrate in the rest of this talk is sort of a top-down empirical approach with, if there's a mantra to it, it's that good problems produce good science. Now, of course, this isn't unique to robotics or computer science. This has been true in many other areas. The Wright brothers, their challenge problem was to create manned flight, and along the way they discovered the Bernoulli principle for air. It was known for water, but not for air at the time. The Apollo mission to land a man on the moon, great advances in terms of remote telemetry and body monitoring. The Manhattan Project, which arguably had positive and negative consequences from a social perspective, certainly from a scientific perspective, great advances in high-energy physics and in scientific computing, among many others. Now, one thing about these challenge problems is that all of them have been successfully completed. They reached their goal. I've had the sort of the pleasure of being involved in a challenge problem that's still ongoing, and it has been very motivating in many of these same ways, and that's, as was mentioned in the introduction, RoboCup soccer. And our goal in the RoboCup community, I'm now the vice president of the RoboCup Federation, is by the year 2050 to create a team of humanoid robots that can beat the best World Cup champion on a real soccer field. And we always, in AI, we've learned long ago, when you're going to make a prediction, use a year that's after you're likely to have retired, because otherwise people will come back and say, "Well, you said." So 2050 gives us time, but also it's also a crazy. It sounds like a crazy prediction in many ways, like how or goal in many ways. Is this going to be possible? People ask, but the amount of time we have. It keeps getting shorter. We're at 35 years now. I used to say 50 years is a long time. Now I have to say 35 years is a long time. But from the Wright brothers' first flight to landing a man on the moon was about 50 to 60 years. From the first computer to beating the human chess champion was about 50 years. From discovering the double helix to sequencing the whole human genome. These are the kinds of things that happen in that time period. So from that perspective, it doesn't seem to me too outlandish to say maybe by the year 2050 we'll achieve this. But nonetheless, we still are in the early stages, and RoboCup soccer has many virtues as a challenge problem. But I think the best way to get a feel for it is just sort of to see what's happened over the years in RoboCup soccer. So first of all, I'll say that there are many different leagues in RoboCup. There's the small-sized league that has the sort of Rubik's Cube-sized robots. There's the middle-sized league, simulation, humanoid. I'll show you some videos. But the thing that's common among all of them is that there's no human in the loop. So in the first year, in 1997, this shows 4 of the different leagues. This is the early Sony IBOs. This was in 1998. And you see the robots, they fall over. But when they did fall over, they were able to get back up. The robots banged into walls sometimes, but they also scored goals. Here you'll see a goal scored. There wasn't much opposition from the defenders or anything, but it happened. And the thing here, you have to recognize, these are sort of painful for me to watch now, but back in 1997, most roboticists didn't have robots. They worked on one part of the problem. They called themselves roboticists, but only worked on the planning or only worked on the vision. Getting this whole loop closed was a significant both engineering but also scientific challenge to figure out how can you make that happen in real time. Now, jumping forwards 10 years from there, so still now 10 years in the past from now, you can see huge progress. So some of the same leagues from the previous video, but the individual robots were much quicker. There was now starting to be passing. Down in the small-sized league, the ball was now moving in 3 dimensions. They were chipping the ball. The humanoid league was just at its beginning, so they were just doing penalty shot contests in those years. But now you see the humanoid robots if you go watch the videos of the latest RoboCup competitions, and these ones are also now looking like these other leagues. And there's multiple robots. They're passing. They're moving much more with much more agility. So it's a lot of fun to work on this, but it's really we've found over the past 20 years doing this that it has really driven research in many different areas. And from my perspective, in the areas that are most important to me in multi-agent systems, machine learning, and robotics. And so I've gotten a lot of mileage out of the problems that have been inspired by this. And there's been lots of publications, lots of PhD theses. None of them are about winning robot soccer or winning a game. It's all about, so one of my first students had a PhD thesis that was on robot vision in changing lighting conditions. And trying to get the vision to be robust to changing lighting conditions as still as the images were coming 30 frames per second. And this was very different than what people did in the computer vision community, different from what people had done in the robotics community prior. It was inspired by RoboCup, but then ended up focusing on a much more general and broadly applicable problem. Probably the first PhD thesis in the area was as far as I know, my own in 1998 on layered learning. This was a hierarchical machine learning method that was designed for domains that were too complex for tractably mapping state features directly to outputs, where a hierarchical subtask decomposition was already given. It's actually a very good problem also to try to automatically figure out what a good subtask decomposition is, and people have been working on that in more recent years. But the key was that there was machine learning used at these various layers where each one fed directly into the next one. So you can imagine having learning of some individual behaviors and using those to feed into multi-agent behaviors, team behaviors, and so on. I'm skipping a lot of the details, but I'll say that in the simulation league of RoboCup, we used layered learning to create different learned layers, ball interception, teaching a robot to be able to intercept a ball using a neural network, pass evaluation, which was the problem of if I pass to a teammate, will they likely receive it or not? We used a decision tree to train that. And then had to develop a new algorithm for pass selection. Where should I pass when I have the ball? And this led to, I think to show this, let's see. Yeah, here we go. This led to the team. My team was here in yellow. This was the finals of the 1999 robot soccer competition. No, my team was in red, sorry. And this is what the simulation league looked like at the time. The players are each controlled by a completely separate program, so it's not one program controlling them all. So they have to communicate. Here you see like a multi-agent plan. The ball goes out of bounds. They set up for where they're going to, the sequence of passes they're going to execute, and ended up scoring. Our team here ended up winning the competition, scoring 110 goals over 8 games and conceding none. So it did fairly well in the competition, but then the following year, there were already teams that could beat it, and that was a good demonstration of the sort of progress that happened through RoboCup. We then took the layered learning and applied it on some real robots for walking and ball control. So on the left here, you see some Sony Aibo robots that were learning using a method, a type of reinforcement learning, to learning to walk as fast as possible. And so what they're doing, I'll give just without showing the details on a slide, I'll describe. We parameterize their walk, so the legs of the robot are going through a particular shape, a half ellipse. And we use inverse kinematics, so we basically reason about where the tip of the leg should be at any given time, and then use inverse kinematics to convert that to joint angles. And that leads us to a parameterized trot gait. So the front right and back left leg were moving together, but now we just specified that it would move through a half ellipse over and over, but that leaves 12 different parameters. For instance, how long is the base of the ellipse, how high is it, how far out from the shoulder, the height of the robot off the ground, things like that. And typically people would hand tune these parameters. They would watch the robot and say, let's try a little longer, let's try a little faster, let's spread the legs a little more. We developed an algorithm that would allow the robots to do this automatically and through practice. So here they're experimenting in that parameter space. They're charting how long, they're keeping track of how long it takes them to walk across the field, and then they're experimenting by changing these parameters in various ways, basically a gradient-based method, so trying around a local point in the parameter space, trying some small perturbations of each of the parameters, fitting a gradient, and then taking a big step off and trying something new. Trying to make this work on real robots meant that it had to happen very efficiently. After about 3 hours, which was about 1,000 traversals of the field, these robots had developed a walk that was about 15% faster than anybody had created by hand on these same robots around the world. And by the next year, the paper that we published on this method, everybody was using this in the robot soccer competitions, was using learning to develop walks. And on the other side here, you see the robot learning to control the ball. Here, it's the layered learning aspect is that after learning the walk, it then has to couple that with a behavior of pinching the ball under its chin, which depends on the learned walk. And again, the robot is doing this learning without a human in the loop. So we can, my students could go out and eat lunch or start working on their next paper while the robot was learning. So that's an example of a sort of a contribution that was motivated by RoboCup. More recently, we've been a part of the 3D Simulation League, which is now, instead of those little circles in 2 dimensions, we're now working in a physics-based environment, a 3D simulation league. We developed a parameterized walk, but now for a humanoid robot, in a simulator that looks like this one. And again, we actually, in 2011, we won the competition, scoring 136 goals and conceding none. But this is what this simulator looks like. There's simulations of a now robot, which is a standard humanoid robot. because it's a physics simulator, the robots do fall over, and you have to get them to get up, to walk. Same kind of method for learning. The walk that we applied on the IBOs was applied here, and we developed a walk that was so robust that it ended up scoring most of its goals like this by just walking the ball into the goal. It never actually passed or shot, and still scored the 136 goals. The basic method, again, was this sort of, it's similar, it's called CMAES, where you have a bunch of points in your parameter space, you evaluate them, and then you move along both it's a derivative-free numerical optimization method where candidates are sampled from this multi-dimensional Gaussian, and you keep changing the location of the Gaussian in your parameter space, where your mean in the next generation maximizes the likelihood of the most successful instances in the previous generation, and your covariance maximizes the likelihood of the successful step. I'm going to skip, just in the interest of time, I'm not going to show the progression of the learning here, but this is something I could talk much more about if you're interested. I talked a little bit already about the need for research in robot vision and how that's also motivated by RoboCup. There's been a lot of progress in computer vision on things like shape modeling, object recognition, and face detection. But for a robot, there's many different constraints. And the best way to get a feel for that is to see what the world looks like through the camera of a robot when it's playing soccer. Here's through the camera of one of those IBOs, one of those robot dogs, as it's walking up to the ball and kicking. And so this is basically the input to our robot soccer programs, is one of these images 30 times per second. And of course, what's an image but just an array of pixels? So it's really an array of numbers flashing as input 30 times per second, and the output is the joints of the robot. That's what you should think of as the overall input-output challenge for robot soccer. So within the robot vision challenge, the first thing we do is try to segment out the images, segment out the locations, and as I mentioned, one of the challenges is to do this in a way that's robust to changing illumination conditions. And so here you can see successfully detecting the goal in the ball after that first process of the entire program. Of course, then, once you see those objects in the ball, you have to do localization, figure out where the robot is, the decision-making, and the actions. So rather than talking more about these, I'm going to show you the complete finished product of our team. We sent some highlights to Fox Soccer Channel. They took some poetic license and created this video. RoboCup doesn't actually have the kind of fan support that they're going to show here. We don't play in stadiums like this, but the games do look like this. So the thing you're going to need to keep in mind here is these robots are playing. They're completely autonomous. There were 4 robots on each team, and once the game started, we're all hands off. So the robots are doing all the parts that I showed you. They're doing the computer vision. They're doing the localization, and I like this clip here in particular I like because you'll see the robot walks up to the goalie. When it gets there, it gets bumped, and so its direction changes, but it knows enough which direction it's facing to know that it should kick the ball sideways now with its head into the goal. And here you see it's doing the learned the chin pinch as well to be able to control the ball, which I showed the learning of previously. Here you'll see our goalie making a save as well. Like I said, it's all our highlights. We didn't show teams scoring on us, so we showed the goalie making a save here. This keeps going, but let me stop it. When Sony stopped making the IBOs, we then moved to a humanoid robot, and I showed you the simulation of it, but we've now moved to, we actually use participate in the standard platform league. I should say that league, by the way, everybody had the same robots. There are some RoboCup leagues where people build their own robots, and those are more designed for electrical and mechanical engineers. Computer scientists like myself tend to gravitate to the standard platform league where everyone has the same hardware, and it's the software that makes the difference. So we participated in that. The Standard Platform League moved from the IBOs to the NOWs, the humanoid robots, and in 2012 we won the international competition there. When we came back, they lit the tower on the UT campus orange for us, which they usually only do when the football team wins. So that was a nice achievement for us. But here, this is what these games look like nowadays. So these are very many of the same challenges that we have with the IBOs, the vision and the localization. But now, of course, the locomotion, the walking is much more difficult. And the kicking, but again, they're fully autonomous. So this was the finals. We were playing against a team from University of Bremen. This was they had won the competition the last 3 years, and here's our robot in the finals going in on a breakaway and scoring our first goal. We ended up winning the game 4-2. But again, we've had to it's always a big this video is online with all the in all its glory. But we've had again, it's continuing to motivate us to work on now robot locomotion and how can we get humanoid robots to walk. And there's other changes that are happening continually through the environment. There's now the field is bigger. There's more robots on the team. They've now, rather than having one goal be blue and one yellow, they're now both yellow, which sort of requires the robots to break symmetry. We do that by having them communicate about which side of the field they think the ball is on. And they can then coordinate through that to figure out which way they're facing if they fall over and get back up. The other thing we do, I said that our goal is by 2050 to create humanoid robots that can beat the best World Cup soccer team on a real soccer field. We still have a ways to go, but since 2007, some non-professional soccer players, some sort of aging, middle-aged soccer players like myself, have played against the champion of the middle-sized league. So I'm here playing against the robots with some of my colleagues, and every year the winner of the competition says, "Oh no, we can't possibly put people on with these robots. They're going to be much faster than you. They're going to hurt you. You're never going to be able to keep up with them." And then we get on, and it turns out that we're still the people are still much better at being able to pass. I ended up getting called for offsides there. They didn't count the goal, but we are at this point where we can now benchmark against the best robots on real fields, and it's definitely getting it's getting more and more challenging. Maybe because we're getting older, but that's a different story. So I've talked so far about robot soccer. It's of course not, that's been a challenge problem that I've worked on, and it's been one of the challenge problems that I've worked on. But of course, it's not the only one, and I've sort of motivated this style of research. I've also done work in several different areas: trading agents that bid in auctions and coordinate and interact with one another that way. I already showed you some of our work on autonomous vehicles. Autonomic computing is a great challenge problem for AI and computer systems working together. Computer systems that are able to diagnose failures and self-repair. And also, we're moving now towards socially assistive robots. There's also, as I mentioned, there's different arms of RoboCup. Jay Modi was a part of RoboCup Rescue, a disaster rescue scenario, but there's also a RoboCup at home competition, which works on more robots in domestic environments, trying to push the boundaries towards ubiquity. All of these problems, which are the ones that I've worked on, do drive research in some of these sort of low-level building blocks that I referred to at the beginning of the talk. And in particular, if you're particularly perceptive, you'll notice that in these ones, that all of these have two things in common, which is that they all do have some kind of drive towards better machine learning and multi-agent systems, which is why I particularly have chosen these problems. So in the time I have available, and actually let me ask, how long should I go? We started a little late, but I don't know. So keep it to 10 minutes. So I am going to be skipping through some things. I'll focus a little bit on. I'll maybe give again. I'll flash some of these things through, and I'll be happy to talk more offline. But we focused a lot on some details of how to get robots to learn. And I'll just give you a brief appreciation for this type of machine learning we use. Machine learning is a pretty broad field, and area that's probably most commonly known is known as supervised learning, which, a typical problem there is given a bunch of digits, for instance, can you classify which is the 4, which is the 3? You get a bunch of training examples, and then you have to, you get some new examples that you haven't seen before, and have to try to generalize. This is a fairly mature field. There's toolkits out there. There's one called Weka. You don't have to know anything about the details of the algorithms to be able to do supervised learning. You can just download Weka, input your problem as a set of features, and it'll run the algorithms for you. But for robots, there's a different type of machine learning that's more appropriate, known as reinforcement learning. In reinforcement learning, the paradigm is you don't get a bunch of labeled examples. Instead, you have an agent, an autonomous agent, that is learning a policy, which we represent as a mapping from states to actions, where in every given state, you have to decide what action to take. And then when you take the action, you don't get a label like that was the correct action or that was the incorrect action. Instead, you take a sequence of actions over time, and what you see is the effect on the environment. In other words, you take the action, and then you find out what the next state is. And you also possibly get a reward along the way. And so this, so you can think of this as, you're familiar with this if you're trying to learn how to play chess, right? Unless you have a grandmaster standing over your shoulder who nods or shakes his head after every move, really you take a whole series of moves, and at the end you just find out whether you won or lost. Okay, and that's the kind of thing that our robots need to do instead. They don't get these labels. And so this can be formalized as a Markov decision process, and that's how it commonly is. There's a set of states, there's a set of actions. Every action has a probabilistic transition to the various states, and possibly a reward that gets emitted if you happen to transition to a particular state. And your goal is to come up with a policy that maximizes your expected reward over time. So you have to figure out which actions to take from which states so that you have the highest probability of getting positive and more positive and less negative rewards. So there's some foundational theoretical results that really invigorated the field of reinforcement learning. But to be able to scale this up to real robots requires some additional new research. So the main theoretical foundational results were back in the late 80s, early 90s, an algorithm known as Q-learning, which is actually quite simple conceptually, but really elegant from a theoretical perspective, proved that you can actually find the globally optimal policy of a Markov decision process through experience. Doesn't get stuck in a local optimum. Using a very straightforward update rule that keeps track of an intermediate data structure known as a value function that maps your states and actions to a reward. So given a state that you're in, if you were to take this action and then act optimally afterwards, how much reward would you expect to achieve? And if you can learn this value function correctly, then the optimal policy becomes easy to read out. You just look at when you're in a state, you just see which action has the highest value. And it turns out that you can find the optimal value function by just doing an incremental learning update based on the current state, your next state, the action you just took, and the reward you just got. And so this is great that you can find the globally optimal policy. The problem is that you have to be able to represent each of your states and actions as a discrete entity. And so you need what's known as a table-based representation. That's often not possible in a continuous world. For instance, in robot soccer, there's not a finite number of states you can be in. And also the theoretical results require that you visit every state infinitely often, which is never possible in practice. So there have been a series of advances, and I'm going to, in the interest of time, skip through these. One is just to give you the pictorial view. Rather than representing it as a table, you can fit a continuous function, what's known as function approximation. Now you can generalize to states you've never seen and maybe do a one-dimensional search over the action space. Another thing that people have done is rather than doing an incremental update on every action, storing all of the past transitions in a batch and then be able to use your experience much more efficiently. And these have allowed us to get closer towards some applications. A famous one in the field was by Jerry Tesaro, who created a human champion-level backgammon player through self-play using reinforcement learning. A colleague, Andrew Eng, created a helicopter controller. It's able to fly a helicopter upside down in a circle, which is apparently a hard helicopter control problem. I'm not a helicopter pilot, but this was also done through reinforcement learning. There have been some great applications. Recently, a colleague of mine, Joel Pino at McGill, has used reinforcement learning for adaptive treatment of epilepsy, and there's been some work on invasive species management and wildfire suppression by Tom Diederich at Oregon State. So reinforcement learning is becoming it's moving towards a useful tool, and I've contributed a bunch in this space. We've been working a lot on human interaction. So I won't show this video, but a student of mine, Adam Sedepin, used a demonstration where he put on a motion tracking suit and used that to demonstrate motions to a robot and had it copying him and learning what to do based on that. My student, Brad Knox, who's currently a postdoc at MIT, he's on the job market this year, actually, did a lot of research on, let me see if I can skip it into here to show, yeah, so using positive and negative feedback. So he's training this robot, the robot is acting randomly at first, and he's just saying good job or bad job, just a positive or negative reward signal. And in the end, he was able to train the robot to do several different behaviors, such as following a person or avoiding a person or keeping conversational distance, using online reinforcement learning. Let's see, I'm going to skip through some of these. I think the one thing I am going to spend some time on is the most recent PhD thesis from my lab. It was done by Todd Hester, who's now works for Nest. Well, I guess now he works for Google also. Google bought Nest. Anyway, he focused on a reinforcement learning algorithm for real robots that works both in real time and with both real time, both from a sample complexity perspective, which means from a small number of experiences, and from a computational perspective. So it has typically been a trade-off. Either you have a computationally cheap algorithm, but you need tons and tons of data, or you have a fairly efficient algorithm that can learn from a small amount of data, but takes a lot of time to train. His TextPlorer algorithm has the following features. It's both sample efficient, real time, can deal with continuous state and delayed effects. And the key insight here was that if you're going to have a robot learn in real time, it can't possibly explore everywhere. It's not going to be able to find, what you give up is then you can't guarantee that you're finding the optimal policy. But if you can reason about what parts of the world or what parts of the state space are not likely to be beneficial based on your model of previous states, you can be much more efficient. I give the example, we as people have to do this very same thing. There's an office building I can see outside the window from my office, and I've never gone into that building because I have a model that it's probably just like all the other buildings around. I instead spend my exploration time farther away from home. And so we developed a computational way of doing this. By only exploring states that are both uncertain in the model and promising towards the final policy. We used a random forest model that basically takes all of the data that we have and divides it into subsets and of training experience and use this to model the variance in what they would predict. So in other words, you have a large batch of data that's given to the robot. You give parts of it to the same machine learning algorithm, and then see in which cases in which states does this different data lead to the same prediction, and which states does it lead to varying predictions. And the algorithm is driven to explore in the parts of the state space where they would predict different things. We tested this in a new domain called Fuel World, where most of the state space is predictable. So in other words, if the robot is somewhere here, or the agent is somewhere in the middle, the actions are going to do the same thing, more or less. It's going to move you up if you take the north action, and down if you take the south action. But there's a bunch of fuel stations around the top and the bottom that all have varying costs. And so conceptually, what you want the agent to do is here's the start state, here's the goal state, and it can't get there directly. You want it to spend most of its time exploring the costs of the fuel stations, and to build a model aggressively of what the world's going to look like in the middle of the environment. And I think I have a video of what the learning ends up looking like. In principle, as far as the agent is concerned, there could be a fuel station anywhere here in the middle of the environment, right? It's not told that everything generalizes, but it learns fairly quickly from experience that these fuel stations are on the bottom row or in the top row, and after having sort of built a model of what the world looks like in the middle, it spends most of its time exploring that part of the environment, using this approach that I talked about of splitting up its training data into batches and seeing where the variance is. And it finds that most of the unpredictable things happen on the edges of the environment. So again, I'm not going into the details here, but the trade-off here is that previous algorithms had either overexplored, been exhaustive throughout the entire state space, or they've underexplored and instead focused very closely on the start state and never actually gotten to the goal. Another component of this was being able to do this in real time. So we created a model, an architecture that does the model learning, the predicting the effects of your actions, the planning, and the acting all in separate threads so that they can all happen concurrently in real time. And we've released this now as a open source package as a part of ROS, Robot Operating System. So anybody now who wants to take a robot and do reinforcement learning in online planning is able to take our source code and work from that. This is sort of a step in the direction of WECA for supervised learning now having a publicly available and open source package for reinforcement learning on robots. And the key sort of demonstration of this was on our autonomous car. We were able to show the car learning a speed control task. Here it was trying to be able to maintain a speed of 15 miles per hour, where we didn't initially tell it what the effects of pushing the accelerator or the brake was. It had to learn that. It had to explore and build a model. And it was able to do that in 2.5 minutes of real-time control. In other words, it didn't first explore and then do some computing offline. It did all its learning while it was driving. And so this was the mix of sample complexity and computational complexity, and was sort of the key demonstration that TechSplore was able to work on a real robot. Okay, so just to pop up one more time, I've talked about, I motivated the complete solutions to relevant challenge tasks. Talked a little bit about robot learning. I'll just do 1 or 2 slides about the multi-agent reasoning aspect that comes into this research, and then I'll wrap up. So, first of all, I mentioned that a high-level goal of AI is robust, fully autonomous agents that work in the real world. And the key is, key observation is once there's one, there will be many. If you have your autonomous car, so will the neighbors. And to coexist, these agents are going to need to interact or learn. And so I showed some videos previously of the DARPA Grand Challenge and the Urban Challenge. It's clear that it's clear to me that autonomous cars are in our near future. So we've spent a bunch of time now thinking about what will be the impacts of autonomous driving on our urban infrastructure. And in particular, at intersections, are we still going to need traffic lights and stop signs? Or can we do better by having the cars interact with one another? And so here's a simulation of what we think the world will be able to look like. Here, each of these cars is independently controlled, so there's not a single program controlling all of them. Instead, they're each deciding when they're going to arrive at the intersection. They're calling ahead for a reservation in space-time, and there's an autonomous agent at the intersection that's maintaining a reservation table to make sure that there's no collisions between the cars. So sometimes a car has to wait. It doesn't have a reservation yet, but once it gets one, it has a guaranteed path through the intersection with no collisions. Now, we can make this happen in simulation. people ask, does this happen in the real world? I often show this video of traffic in India, where the difference here is that we can guarantee that there's no accidents, and in these intersections there are many. The other thing people often say is, well, that's fine and good in simulation. What about on real cars? And we actually have deployed this on a real autonomous car. This is a video from inside. If you were sitting outside of here, you would see our autonomous car. We just have one. And so when it comes up to the intersection, you wouldn't know why it's stopping or going through. But we built a mixed reality setup where it's actually simulating many other autonomous cars. So this green one here is a proxy in the simulation for where the car is in the real world. When it turns blue, it got its reservation to be able to go through the intersection and not collide with any of these other simulated vehicles. So we're getting to the point where we can experiment not just in simulation, but actually figure out how big do the buffers need to be to make sure the car can interact safely. And now we've continued this research by scaling up to grids of intersections and thinking about, well, now can we actually do dynamic lane reversals? So this is a simulation showing what happens if with autonomous cars. We could now say, well, you have a road with 3 lanes going in each direction. If there's a lot of traffic going in one direction, we could actually shift over and have 4 in one direction and 2 in the other, and do this actually on a minute-by-minute basis. In a way, people can do this now, rush hour in and rush hour out, but with autonomous cars, there's a lot more possibilities opened up. And so we've been looking at those issues as well. Also, I have 2 students now working in doing their thesis research on an aspect of teamwork that we've called that we're calling ad hoc teamwork. A typical teamwork scenario is a team gets to practice together and do sort of a lot of pre-coordination and figure out how they'll work together. In ad hoc teams, in contrast, and I'm not going to go into any details here, your teammates are out of your control, and they're likely to be suboptimal. People can do this, for instance, playing pickup soccer or playing pickup basketball, but we're trying to, as we get to a point where there's going to be robots everywhere and autonomous agents everywhere, they're going to need to much more frequently be able to interact with what we call ad hoc teams. And this is going to require a lot of actual plan recognition, not for adversaries, but for teammates. The goal of this line of research is to create a good team player. I introduced this as a challenge problem to the AI community a few years ago. We've worked on it both from a theoretical and empirical perspective with recent articles. There's now been some experiments at the robot soccer competitions last year where we did pickup games of robots, where we took one from each team and put them on the field and had them try to play together. That was, there wasn't much advanced warning, so the robots just sort of did what they normally do. This year it's an official challenge event, and people are starting to think about how can they make a really good challenge or pickup or ad hoc team player. And there's also a workshop at AAAI now that's going to focus on this topic. Okay. So I know I've gone through very quickly a lot of material. I know I've skimmed over a lot of the details. But I can't finish a talk like this without at least one slide on the implications. I've said the long-term goal is to create robust, fully autonomous agents in the real world. And I think it's important that we also ask what happens when we achieve this goal, or if we achieve this goal. You know, there have been some utopian views, like the Jetsons, but of course Hollywood has often had a different perspective. And of course, just like any technology, there are both positive and negative possibilities for use of these kinds of technologies. The way I like asking this question, and we're not going to have time to answer it here, but I encourage you to have this discussion, is ask people, would you rather live 100 years, would you rather have been born 100 years earlier than you were or 100 years in the future? And the answer to this, I think, is not necessarily straightforward. There's you know, in a room full of computer scientists, usually people will jump at the 100 years in the future. But it's not long usually before people, you know, some people will point out we don't know if the world will exist 100 years from now. There's a lot of dystopian possibilities. So it does require a little bit of a leap of faith. You know, so I wouldn't be doing what I'm doing if I didn't think that these kinds of technologies, robotics, autonomous agents, machine learning, multi-agent systems, were part of the solution and part of making our world better in general. But I think we do have a responsibility to ask this question and talk about it deeply. This work was joint work with many of my former students, as shown here, and some of my funding agencies. But just to summarize, in this talk, I've discussed creating sort of the long-term sort of thread for the research in my lab is creating robust, fully autonomous agents in the real world, with the goal of building complete solutions to relevant challenge tasks, with the idea that good problems drive good research. I take the approach of combining algorithmic research with problem-oriented approaches, and have tried to emphasize that some of our biggest, most pressing challenges are in machine learning and multi-agent reasoning. But I'm doing one small part in, I think, a field's worth of research. I think this is very much in line with the spirit of the research and the goals that our colleague Jay Modi also pursued in his research career. And I think it's been a loss for the field that he's no longer with us. But we're doing our best to push forward and to try to achieve these long-term goals. So with that, thank you for your attention, and I'll be happy to answer any questions. Yeah. So that's a very good question. And so just to people hear the question, it was, what are we assuming when we show the cars going through the intersection? We started doing this research back in 2003, and we said, when we did that, we said, we're going to assume that the cars are autonomous. And people would look at us like we were crazy because nobody thought that autonomous cars were coming. I think nowadays people are more accustomed to that thought. But we were very careful to make sure that we only built in assumptions that were possible with current technology at that time. And so what that means is the cars are, they are aware of their own location through GPS. And so our autonomous car that we had in the DARPA Urban Challenge used GPS and was able to know where it was within 50 centimeters. So that's enough to know what lane you're in. But they did not know where all the other cars were. They only also knew the distance to the car immediately in front of them, which is also possible. The adaptive cruise control has that kind of technology. And then the communication is not between each car, but between the car and the intersection. And we assume that could happen within about 300 meters of the intersection. And there's a technology, dedicated short-range communication, DSRC, which has become an industry standard for that type of range of communication. But all of the messages are within the constraints of what's possible with DSRC. The sensing is local sensing, just the car's own location and the distance to the car in front of it. And all the decision making is distributed. Each car is deciding what to do. And so that was actually one of the key technical challenges in that research was how do you, what's the protocol that will be there for the communication between the car and the intersection, and what's the interaction mechanism that would stay true to those sort of realistic constraints. Yeah, Dario.
Great talk. It sounds like the current state of the art is, in general, you're assuming the same policy for all the agents in the system, at least for a lot of the stuff you talked about. I was wondering what you've learned, maybe what the community has learned about having different policies, and I would think long-term for most of these domains you would have not only humans in the loop, but also machines with different versions. So if you took your 2014 robot and made it play with your 2004 robot,
Mm-hmm. Yeah, so that's exactly the motivation between this ad hoc teamwork challenge that I talked about, which is the idea that there are going to be legacy robots, or there's going to be agents from different research groups when there's a disaster, an earthquake or something. People bring their robots from different places, and they need to be able to interact with one another. And so our first take towards this has been to treat that like number one, a plan recognition problem. So trying to actively observe and model the other agents, not necessarily assuming that they're like me, but rather build a model of their capabilities and their tendencies. I mean, what you would like, and we've done some experiments, some of the initial experiments in this direction are, We took a multi-agent problem, a standard one in the field called the predator-prey domain, where there's 4 agents on a grid, and there's that are the predators, and there's a prey that's moving randomly, and to capture it, they need to get on all 4 sides of it. And we took a class of students, 40 students, computer science sort of master students, and told them each to build a complete team of 4 predators. And they did that as their assignment. We then took those 40 teams and removed 1 agent from each of them and tried to create a single program, a single agent that could fill in as the 4th on any of those 40. And without telling it ahead of time which one it was in. And that's exactly the problem. And the way it did this was by building a model of what are the typical types of other team strategies, and then from a small number of observations, trying to figure out, okay, is this the type of team that each picks a particular spot to aim for, and I have to fill in the 4th, or is it one that is more reactive? And we found that if you just took 1 agent from a team and plopped it into another one, it wouldn't work well. But we were able to build a team that was a single agent that was robust to being a teammate in any of those 40. And so that's, we've learned that it's not necessarily the right thing for them all to do the same thing. And furthermore, even if it is the right thing, they probably aren't going to when you come across them in the real world. So, yeah, it's a great question.
So, being a big fan of the research program of the applied problem driving the whole thing, let me ask you to step up even a level higher than you've been here, and do you have theories about what makes for a really good problem to try to attack? Specifically, I think, if I could direct you a little bit, there are problems that if industry gets excited about it, they'll throw money at it, and it will be solved. It's not necessarily the case that we need a better technical solution.
That's right. No, so actually, I think that's a very important point. I showed video of my autonomous car. I've decommissioned my autonomous car. But when I started working on it, I felt like this was a great research challenge problem. I now am convinced that industry is doing it and doing it well, and it's not my role anymore to be spending time building the autonomous car. I think that there's, especially in computer science, we need to think about what is the interplay between industry and research. I think that the practical problems that have a 2-year horizon or something like that, that's industry's job. We need to be thinking about what, the video of my colleague from Berkeley, Peter Abeel, with the folding towels. Industry's not working on a robot that will fold towels yet. I think that's a great challenge problem. And of course, beyond folding towels, there's a lot of fine motor manipulation. Robot soccer, same kind of thing. It's something that's got at least a 10-year horizon before the technologies are going to be ready for money making. I think is where we're uniquely suited in academia to attack. Yeah.
Somewhat along the same lines, and focusing a little on your ad hoc teams and your choice of the year 2050.
Mm-hmm.
So I was at a conference recently where it's reasonable to think that babies born today could live to be 150 through joint replacements and regenerative medicine, for example.
Mm-hmm.
Probably it won't be smooth, right? There are all kinds of social problems. So this ad hoc team play by 2050 might be a whole lot different than maybe you're envisioning it, in the sense that there may be lots and lots and lots of them, and they have to interact as social beings. Do you have any thoughts about what kind of challenge comes from that sort of thing?
So you mean the robots interacting as social beings? Yeah. So there's a growing field now in human-robot interaction, which is sort of an offshoot of human-computer interaction and an offshoot of robotics. It's sort of the intersection between the two. I haven't personally done a lot of research in that area. I've sort of dipped my toe a little bit with this. My student who I showed, who's doing the interacting with the robot using positive and negative reinforcement. I think there are there are interface and design issues. Just, how do you make something that people are comfortable anthropomorphizing? And I think it's an area that requires some careful attention. I don't have much to say. My research has always started from the perspective of, let's see what we can do with full autonomy, without dealing with the sort of, robots are complicated enough. When you try to put people into the loop, then all bets are off. But I think it is something that's unavoidable. If we're going to make the robots ubiquitous, they are going to be interacting with people, and the interaction design issues are really important. I guess the one thing that we have looked at is what are the kinds of in machine learning in particular, we usually assume that the feedback that you get is generally correct feedback. And when you're dealing with learning from human interaction, now you have to deal with the feedback being much noisier. And so that's when we did do this research in, and not just because people make mistakes giving the feedback, but because if you're learning to match a person's preferences change over time. And so learning, having the robot learn to drive from point A to point B, there's sort of a correct way to do that. To have the robot learn how to, whether to, when to bring you your coffee today or something like that, that's going to be different depending on many different factors. And so we can't just take the algorithms from machine learning and the algorithms from robotics and put them together. We're going to need to have a field that focuses on that from the outset. So, yeah, a good question, I don't have a deep answer to it. Yeah.
I'd like to ask you a question about what your aims are for education in robotics. We have a lot of sort of high school or freshman level robotic programs where the kids see these things, they get excited, and then we have very sophisticated researchers where PhD students. How do you get people from one place to the other?
Yeah, so that's a great question. In fact, I'm going to use that to plug a venture that I've been involved in a little bit. I think right now, it's true, when I was a graduate student, the only way you could have a robot was being at one of the top research institutions. It's now gone to undergraduates and then down to now elementary. Every elementary school student has access to a robot one way or another. But we've been typically using robotics as a tool for teaching about robotics or teaching about computer science. I've been working with a group called Robots Lab that has been trying to use robotics as a way to teach much more broadly math and science. And for instance, they've created actually a really nice, they call it Robots Lab Box, that basically in it has 4 robots, a tablet computer, and is designed so that any teacher who has no background in computer science or robotics can just take it out of the box and start doing basic math lesson plans using these robots. So for instance, one is that they took a quadrotor, an AR drone, which is and you can just buy off of the shelf. It's got a downwards facing camera, and they built a really nice interface so that the robot can go up and down, and on the tablet as it's doing that, you can see the area that the camera is able to see. And they have a beautifully laid out lesson plan to teach the quadratic relationship between height of the robot and area of the square that it can see. And then allow students to be able to say, if you want to be able to see this area, what height does it have to be at? If it's at this height. And I've actually been in classrooms of actually a Saturday detention in high school where the kids definitely did not want to be there. They saw the robot, they saw the concept. One of the students said, oh wait, that's sort of what happens when I take a flashlight and move it back from the wall and the area gets bigger. And within like 15 or 20 minutes, they were all sitting and solving quadratic problems on paper. And this moving from actually seeing it in concrete robotics and then moving all the way to the abstract, I think is got to be the new model for education. I think there's tons of opportunities. Kids aren't going to learn from lectures like this one. Because there's the video of that went viral of the little 2-year-old girl who they handed her a magazine and she tried to make the pictures bigger and tried to flip the page by going like this, right? Kids, when they're 2, interact with media. And so there's no reason to expect that kids are going to learn math and science by reading textbooks and listening to lectures like this one. We've got to create these demonstrations. Robots are perfect for that. And then we can concretize it. So if you... I think it's going to happen more. I do think there is this one example, at least, of Robots Lab that's starting to catch on. I invite you to check it out. But I think education is something that we can really leverage robotics for.
Thanks again, Peter, for a great talk. I'll say a few words. Okay, I was going to start the presentation with a few words about Jay, but I was waiting for his family to arrive. We have with us his father and his brother. Welcome. You probably got stuck on the highway or something. One thing that I was thinking about in your talk is the challenge of 2050 for maybe beating Brazil in the World Cup, and I think that the current robots I saw can give the Philadelphia Union a run for their money. So it's pretty good. I think that what you saw today in Peter's talk represents the type of scholarship that Jay was involved in. He was in the field of multi-agent systems. He was identified as a future superstar in the field, and I think that had he been with us today, he would have been able to give a talk like this. Pragnesh J. Modi was born in 1975 and passed away in 2007. He joined our department as an assistant professor in 2005. So he was only with us for a brief time, a very brief time. He joined us from having completed his postdoctoral fellowship at Carnegie Mellon University, and he was previously doing his PhD at the University of Southern California. He was quickly identified by our student as a superstar teacher, but in the meantime, he was also working on his research, and in the very brief time he was here, he won the NSF Career Award, which is a real designation from the community on someone who's an up-and-coming star. But more than that, Jay Modi was selected as one of the top 10 young AI researchers by the IEEE Intelligent Systems Advisory Board, which is a truly amazing distinction for a young scholar. And his PhD dissertation became one that has numerous citations and has really laid the foundations for his discipline. In recognition of this, the International Foundation for Autonomous Agents and Multi-Agent Systems has named its outstanding student paper after Jay Modi. So I'd just like to say that even though he was with us for a very brief time, we miss him dearly, and it was a terrible loss for us as a community, as a group of scholars, and as a group of professors and students to lose such a bright star. This concludes our program. I think that for those of you who would like to have lunch, we have lunch in the room next door, and you can mingle with Peter, our distinguished speaker, and Jay's family, and our new Jay Modi recipient, Ling. Thanks for coming.